In episode 0, we showed you the numbers. 800 draw calls where 127 would suffice. A landscape fractured by the very algorithms meant to create it. Today, we ask the deeper question, why? What fundamental difference makes one approach produce chaos and another produce cohesion? The answer lies not in marketing claims, it lies in mathematics. Welcome to the quiet craft of optimization. This is the mathematics of wave function collapse. Wave function collapse, or WFC, has an intimidating name. But its essence is beautifully simple. Imagine you have a puzzle. Each piece represents a chunk of terrain, a cliff edge, a river bend, a forest clearing. The pieces don't have freedom. They have constraints. A river cannot flow into a cliff wall. A forest cannot abruptly become a desert. The pieces must respect their neighbors. This is what WFC does. It solves a constraint satisfaction problem. Every tile placed must be compatible with every tile adjacent to it. Not sometimes. Always. Most terrain generators use noise algorithms. Perlin, Simplex, Worley. These are brilliant tools. They create natural-looking height maps with minimal computation. But they have a fundamental blind spot. Noise operates on continuous values. Terrain tiles operate on discrete cells. When you sample continuous noise at discrete points, you lose information. The smooth curve between point A and point B becomes invisible. You only see the values at the points themselves. This creates what we call the discontinuity problem. A noise function says gradual slope, but your tile grid says cliff edge. The mathematics don't align, and when they don't align, you get seams, you get mismatched biomes, you get terrain that looks wrong. Your options? Regenerate and hope for better luck, or patch manually. Neither scales. Wave function collapse takes a different approach. Instead of generating values independently, it generates them dependently. The algorithm works in 3 phases. First, it identifies all possible tiles that could exist at each location. Second, it applies the rules. What tiles can border what? Third, it uses probability to guide placement. Here's the key insight. When you place one tile, you don't just fill that cell. You eliminate impossible options from every neighboring cell. You propagate constraints. This is the collapse in wave function collapse. Each placement reduces uncertainty, and that reduction cascades outward. The result? Every tile placed is mathematically guaranteed to be compatible with its neighbors. Not just probably, provably. And because compatibility is baked into the algorithm, you never need manual fixes. You never need regenerations. The first generation is the correct one. The mathematics underpinning WFC are elegant, but you don't need a PhD to understand the intuition. Each possible neighbor has a compatibility score based on 2 things: how well it fits the current tile and how well it fits the terrain as a whole. The algorithm doesn't guess, it calculates. It computes the probability-weighted score for every possible neighbor at every step. Then it selects the highest scoring option, not randomly, not heuristically, deterministically, based on the rules you've defined. This process naturally minimizes what information theorists call entropy, the measure of uncertainty. Each placement reduces uncertainty. By the time the grid is complete, uncertainty is 0. This is why WFC feels predictable in the best sense. The outcome follows logically from the constraints. There are no surprises because there can't be. All of this is theoretically interesting, but in mobile development, theoretical interest must translate to practical results. When WFC guarantees terrain continuity, you gain 3 advantages immediately. First, you can use larger chunks. If every chunk connects perfectly to its neighbors, you don't need to subdivide to hide seams. Larger chunks and fewer draw calls. Second, culling becomes more efficient. Uniform, predictable terrain frustrums are easier to calculate. You spend less CPU determining what to render. Third, memory overhead drops. No need for adjacency buffers or patch data structures. The topology is implicit in the tile definitions. The numbers on screen come from actual benchmarks on a mid-range Android device, an 82% reduction in draw calls, a 45% improvement in frame time. This isn't hypothetical. It's what WFC delivers. Wave function collapse is not a marketing term. It's not a buzzword. It's a mathematical approach to procedural generation that prioritizes consistency over chaos. In this series, we'll explore how to implement it in Unity, how to tune it for your specific needs, and how to achieve performance that feels almost unfair. Next time, we'll write actual code. We'll build a WFC solver from scratch. We'll show you how to define tile rules, how to implement constraint propagation, and how to integrate it with Unity's terrain system. Until then, remember, good optimization is not about tricks. It's about making the mathematics work in your favor. This is Mobile Terrain Forge, and this is the quiet craft of optimization.